Hello, I'm Sam. Today what I wanted to talk about was pressures. So what I'm gonna do is kind of ramble about it first, like talk about it, talk through it. Hopefully you pick up some of the things that I will be talking about. Then I'll put all that on the diagram to help that sink in. And then lastly, I'll bring some physics into it and hopefully show that all these relationships make sense. So the pressures that we're going to be talking about, some include the peak pressure, the plateau pressure, positive and expiratory pressure. How can I give you some intuition? Well, you can think of the pressure as the sum of the other pressures. Your total pressure is going to be called your peak pressure, your pressure at maximum inspiratory pressure. The sum of the other two pressures that are most important are the pressure and the resistance of the airways and the pressure of the elastance of the alveoli or the lung, and that's called the plateau pressure. Those are the two main important ones. And why are these pressures important and how are they used? It's because we use a lot of ventilators now. We have assist control, we have volume control. And because compliance is equal to the change in the volume over the change in the pressure, when the compliance of the system is the same, when you've set a volume, the only thing left to change is the pressure. That's what the nurses are going to be monitoring. That's what you're going to be called about. That's what ARDS algorithms want you to look at, a plateau pressure, right? The peak pressure you want to be less than 40. Your plateau pressure you want to be less than 30. And I'll be showing kind of how you can think about these and how you can calculate one from the other, the peak pressure, the plateau pressure, and then how you can figure out what kind of problem you have as a result. So a breakdown that is good in a rule of thumb is if it's a plateau problem, then it's a compliance problem. If it's a resistance problem, that's going to be somewhere in your airway, whether it be the tubing, the endotracheal tube, if there's a kink, if there's an obstruction, if it's too small, if there's biting on it, if there's bronchospasms, if there's mucus plugging. For your plateau pressure, one of the problems you're going to run into is something causing your alveoli and lung system not to be able to open up. So this can be from the alveoli, if there's pulmonary edema, if there's ARDS. This can be from intrathoracic cause like a pneumothorax preventing the lungs from re-expanding. This can be from extrathoracic cause such as abdominal compartment syndrome or ascites, where all the pressure is pushing up and your lungs can't expand. So hopefully I've built up some intuition and I want to take it to the whiteboard. So if you think about your circuitry as the vent connected to the rest of the circuit, which is going to be including your mouth, your nose, that's going to go all the way down here into your airways, right? I made this alveoli a little bit bigger than the rest because the alveoli is going to represent the plateau pressure, the elastic pressure, and then the pressure resistance is going to be represented by the airway leading all the way up to the vent. As I said, the pressure of the total, which is the peak, is going to be a sum of the other pressures, your resistance and your elastic pressure. This elastic pressure is proportional to 1 over the compliance, and we'll define it as the plateau pressure momentarily. So you can think of the total pressure in the system as a sum of the pressure of the resistance, things that cause the airflow to not move as well, and as a sum of the elasticity, which is inverse of the compliance. So in a pressure diagram that you would see on the ventilator, you would see something like this on normal inspiration. This would look more like a shark's fin, right? So what you have here is you have the peak pressure or the peak inspiratory pressure, but you don't have any of these other pressures. What you do also have is you have the positive and expiratory pressure. this is the pressure above the baseline that you set on your ventilator. And this just gives some positive pressure to overcome the resistance in the endotracheal tube. So let's think about how we can calculate these two other pressures when we have the peak pressure. The peak pressure opens up the airways and opens up the alveoli and the lung as well. And that's what you get when you get a maximum breath. And that's the peak, and it occurs for only a momentary time. So then if we understand that this peak pressure has put in all the effort to open up the resistance and the elasticity, what we can do is we can tell the machine to just give enough pressure to continue to open up the airway and just keep the airway open and not give any more than that. It had to give an additional pressure to open up to overcome the resistance, but after you've hit the top, there's no more resistance. What I'm trying to get you to understand is that if we want to calculate the other pressures, we can try to knock one other pressure off. So what we do is we do an inspiratory hold, and that gives just enough pressure to open up the alveoli and overcome the resistance, which is going to be 0. So what an inspiratory hold does is it essentially is the pressure when the resistance in the airway is 0 after a maximum breath. So what we see here is this maximum breath, and then you do an inspiratory hold, you give just enough pressure, and then you can overcome the alveoli, and this is called a plateau pressure. Why is it called a plateau pressure? Because after you get maximum inspiration and you're doing the inspiratory hold, it's going to be a straight line of just enough pressure to open up the alveoli, and it looks like a plateau. So basically, a plateau pressure is the elastic pressure, or the inverse of the compliance pressure, when you have just enough pressure to overcome the resistance, but no more than that. So the pressure resistance is going to be 0. How can we represent this as a formula? So the peak pressure is going to be equal to the sum of the resistance plus the sum of elasticity, and that's going to be inverse to the compliance. And at maximum inspiration, that's going to be the plateau pressure. And you also add the PEEP into this equation, but because PEEP is constant and we want to find out ways to troubleshoot the pressures, we're going to assume that the PEEP's not in this equation for the variables that we're looking at. So now we come into a problem of, let's say someone pages you and the peak pressure is elevated. What you need to figure out is whether it's a resistance problem or a compliance problem. So what we calculate is the compliance. If compliance is high and resistance is not high, that means we know it's a compliance problem. However, if compliance is normal, even though we don't calculate the resistance, we assume that the resistance is elevated to make the peak pressure elevated. So essentially, we use one to tell the other. If the peak pressure is elevated and the resistance is elevated, we know that the compliance is normal. So what we see on the ventilator is the plateau pressure. It'll be normal. So then we're ruling out a compliance problem and thinking this is a resistance problem. So let's go into that, right? So let's say we're thinking this is a resistance problem. What we would see is an elevated peak pressure. We would get called for it, and we would also have an elevated plateau pressure as well. And then we're going to assume resistance is normal. So then when we see this, we think compliance issue. If the peak pressure is elevated, but we look and the plateau pressure is normal, then we're thinking this is a resistance issue. All right, so now that we have the arrows, let's put in some numbers to it, right? So if the peak pressure is greater than 40, then we're concerned. We look at the ventilator, we see that the plateau pressure is greater than 30. Then we're thinking, this is a compliance issue. What will we see on the ventilator? We will see a peak minus plateau pressure of less than 10. So this gap will be small. The peak minus the plateau, this difference will be less than 10. What are the causes? Anything that can affect the compliance. It's gonna be extrathoracic, intrathoracic, as well as things that affect the alveoli. So things that affect the alveoli: pulmonary edema, pneumonia, right, pleural effusion. All right, the other things that we would look for is extrathoracic and intrathoracic causes. The extrathoracic causes, these are alveoli. Extrathoracic causes being stuff that push the lung from below, such as abdominal compartment syndrome and ascites. The intrathoracic causes, these are going to be things like pneumothorax, where the lung can't push against the air. So this is all for things that affect the compliance. Now what we're going to look at is resistance problems. So the pressure tracing that you would see, it's going to have a huge gap. It's going to be greater than 10, the peak and the plateau pressure. All right, so what are the causes of a resistance problem? It's everything I told you about the circuitry. Resistance problems are going to come from small ETT tube size, small kinking in the tube. It's going to come from mucus plug. It's going to come from bronchospasm. So if you have COPD or asthma, the patient could have hyperreactivity of the airways, causing it to momentarily increase the resistance pressures, leading to you seeing an increase in the peak pressure. So I think we've gone over a good overview of just what can elevate the plateau pressure, what can elevate the peak pressure, how to troubleshoot when we see elevated peak, how to figure out which pressure it is that is elevated. If the plateau pressure is elevated, we can assume that the resistance pressure is normal, and we can assume this is a compliance issue due to something affecting the lungs or the compliance of the lungs, either through intrathoracic or extrathoracic means. Or if, let's say, the peak pressure is elevated, but your plateau is normal, then we can assume this is a resistance problem coming from anywhere in the airways. All right, and then for this final part, what I want to do is to show you that in this equation, we've related the peak pressure as proportionally related to the resistance and inversely related to the compliance. And what we've also showed that this plateau pressure is inversely related to the compliance. So first I'm going to show that the peak pressure is related to both the resistance and the compliance, and naturally that'll follow that the plateau pressure is only related to the compliance. The reason that resistance is knocked out of the equation goes back to how we measure the plateau pressure. The plateau pressure is measured after you take a maximum inspiratory breath. Then you give just enough pressure that the resistance is no longer in play. The pressure resistance is 0. So all you have left is the plateau pressure. So plateau pressure is measured without, when the system is without resistance. And you can see that. You can see that plateau pressure is measured when the system is without resistance. How we show that the peak pressure is related to the resistance over the compliance is by treating this like a circuit. And it's a series circuit because the pressures are summed up from one another. That's how we're able to sum up all the pressures. So in this series circuit, there's gonna be a voltage source. There's gonna be a bunch of little resistances. There's gonna be a capacitance that stores the charge, and it's gonna be a closed series circuit. And how can we think about these, this as the lung? Well, I'm gonna show you, but first I'm gonna write out the formulas pertinent to this equation. And that's gonna be the voltage is equal to the current times the resistance, and the capacitance is equal to the charge over the voltage. So essentially, what you can think about this is there's a voltage source that sends the current through the resistors to power up whatever you're using, and then there's a capacitor that stores the charges over the certain voltage. So how does this relate to this lung circuitry? Well, voltage, we have voltage, we have current, we have resistance, we have capacitance, we have charge. So voltage in this case is the pressure, the current is the flow, the resistance is going to be the resistance in the airways, as well as the ETT tube and any part of the ventilator to the human system. The capacitance is going to be the compliance, and the charge is going to be the volume. So essentially what this capacitor does, it stores the charge. And what our lungs are doing is we have a very compliant lung that is storing the volume, all right? And it's storing it through the pressure gradients that we have, right? So this pressure is going to come from the voltage source, goes to the parts that it's trying to power up, which is going to be the alveoli, it's going to be the lungs, it's going to be the bronchi, right? And from this equation, we can see that the pressure, the peak pressure, is related to the resistance and the compliance. How do we see that? Because we said the voltage is the pressure, right? Peak pressure is directly related to the resistance. And we showed that the compliance, we're saying compliance is equal to change in the volume over change in the pressure, right? So here we have the pressure. If we moved it up here, it'd be inversely related to compliance. Pressure is in the denominator, compliance is at top. That's how we can show this. And we showed plateau as pressures when there's no resistance, because you've given just enough pressure to overcome all the resistance. Plateau pressure is looking at the pressures without when resistance is independent. So I hope that kind of showed you that the relationships we have here maintain steady even when thinking about this as a circuit. And then when we are troubleshooting pressures in a ventilator, that if we know the peak pressure and the plateau pressure, then we can kind of reason whether it's a resistance or a compliance problem. And that can help us when we're working with ventilators on volume control mode to basically figure out if the patient is going into a compliance problem, if their ARDS is worsening, if they got a surgery, if they've gotten an abdominal compartment syndrome. And then if it's a resistance problem, we can kind of troubleshoot that by, if it's like something with bronchospasm, we can give inhaled bronchodilators. If it's ETT tube problem, that we can suction it out, like figure out if there's any obstructions, unkink it. If there's a bite, if the patient is biting the tube, then we can give them a bite block. So I hope that this will help give you more intuition, better understand peak pressures, better troubleshoot the ventilator.